Imagine you're in a high-stakes technical interview. The task is to reverse an array containing 10 million records, and you have to finish it in 20 minutes. The standard instinct is to create a second array and push elements into it, but this doubles the required memory. On massive datasets, extra allocation causes a crash. To pass, you must manipulate data within its original borders, what engineers call in place. Prioritizing space efficiency ensures algorithms remain stable even as datasets scale to millions of records. The opposite ends approach is the industry-standard technique for handling these memory constraints. We begin by initializing a left pointer at the start of the array, index 0. Setting the right pointer is where many candidates slip. If you set it to the total length of the array, you target an index that sits just outside the dataset. Because of zero-based indexing, the final element is located at the array's length -1. We lock the right pointer there to stay within bounds. Establishing these starting boundaries provides the stable foundation needed for the algorithm to run safely without memory errors. With the pointers in position, we swap the values held at the left and right indices. The left pointer then moves inward by 1, while the right pointer steps backward by 1. We repeat the steps, flipping the outer elements while keeping our memory footprint at 0. Let's pause. What specific instruction tells the loop to stop? If you use a generic loop based on the total array length, the pointers will cross each other and begin re-reversing the elements back to their original, incorrect positions. A strict while loop where the left pointer is less than the right pointer creates a safeguard, stopping the process the moment they meet in the middle. We can translate this mental model to code by representing the pointers as simple integer variables. Inside the loop, a temporary variable facilitates the swap, while the code increments the left index and decrements the right index. Since the pointers only sweep across the dataset once, the algorithm completes in linear O of n time. And because we performed every swap inside the original borders, we achieved constant O of 1 space. This logic is a frequent test of spatial awareness during technical screenings at companies like Google, Amazon, and Meta. Building the habit of minimizing memory usage turns a basic solution into an optimized performance, setting the foundation for every future two-pointer challenge.